So, well, as you heard, I think the reason I'm giving this talk is in part because of this last year's Nobel Prize. And I think the person I shared with, Serge Haroche from Paris, I think we both feel that this award more recognizes our field rather than our individual accomplishments, because there's so many people in this area of quantum control that are doing very good things, and it could have easily gone to many other people besides ourselves. So with that, let me just say a little bit about this idea of Schrödinger's cat. So Schrödinger, of course, was one of the inventors of quantum mechanics. You know, I always admired his courage because he, as fantastically successful as the theory of quantum mechanics has been, he realized that there was some strange things about it. And one is that this idea of the cat, and basically that what bothered him was that even early on, the quantum mechanics was able to describe small systems, atoms, and so on. But there's no reason that it shouldn't apply on a large scale. So to sort of explain his discomfort with the theory, that it should scale to, or should apply also to large scale, he cooked up this example. So Schrödinger's cat example was he has a cat here in a box that's sealed from the rest of the world, the universe, and inside this box is also a single radioactive particle, and if the particle decays, it triggers some mechanism which releases poison and kills the cat. Well, in principle, of course, this is impractical, but in principle, we could write down the quantum mechanical equations that describe this situation, and basically all quantum mechanics tells us is after a time, the so-called half-life of the particle, it has a 50% chance of decaying. All we can say is that the theory says that the cat is neither dead or alive. It's both dead and alive. And so for those non-physicists out here, we represent that by these symbols, the so-called wave function, which represents an equal part where the particle is undecayed, the cat is alive, and the particle decays and the cat is dead. So it's neither one or the other. It's both in some sense. And I think there's a nice analogy to this idea of superposition. This is one pictorial example. And if you look at this box up here, if you kind of adjust your eyes in different ways, you can either see this face be in the foreground, like down here, or this face here be in the foreground. And there's sort of this ambiguity about what state this box is in. And this is very much like superposition and quantum mechanics, that this box up here has both properties simultaneously at the same time. Another nice part of this example, I think, is that when you tend to, if you're looking at the box and you tend to see it in one orientation or the other, that's very much like a measurement in quantum mechanics. We know that when we make superposition states, we can have it be both, represent both properties at the same time. But when we do a measurement on a quantum system, it tends to collapse or project it, we say, into one situation or the other. So you want to keep that in mind as we go along here. So you have to play along with me here a little bit, but an analog to this idea of entanglement is the following. If you think about our boxes again, at least for me, at some instant of time, if I see this side of the box being in the foreground, I tend to see the other one in the same orientation, and simultaneously, or conversely, when I see this face be in the foreground, I tend to see that face in the foreground. And this is very much like the idea of quantum entanglement, where if before the measurement, it has both properties at once. And that's very much like this example of Schrödinger's cat. Before we look inside the box and see whether the cat is dead or alive, it represents both states. So the state of the radioactive particle in that case is correlated with the state of the cat, much like the states of these boxes. So I think that's also an useful example. So as I say, Schrödinger was bothered by this extrapolation of this microscopic theory to the macroscopic world that we live in. And so he puzzled with this throughout his career. And in the early 50s, one way he decided, he explained, well, maybe we're fooling ourselves thinking about these thought experiments in the microscopic world. And he said, in this paper in 1952 is, well, we really never can experiment with just one electron or atom or molecule. And we can consider this situation in thought experiments, but this invariably entails ridiculous consequences. For example, the cat, when we scale the theory up to the macroscopic world. But in fact, this is the world we now all play in, that we can actually play these games, these thought experiments, at least on a small scale. So what we need to be able to do that, you'll see, is we need precise, not surprisingly, very precise control of these systems. We need to isolate the systems as best we can from the environment, like this idea of the sealed box for the cat and the radioactive particle. So we can do this with small groups of particles, and we can't do it with objects the size of the cat yet. But we're still stuck with this situation. There's no obvious reason why it shouldn't scale to the larger world. There's certainly technical problems to realize systems the size of a cat. But in principle, we don't know why we shouldn't be able to do it on some large scale. So as I advertised in the abstract here, this is going to be close to what in the Nobel lectures, what they would like you to do is tell a story of why you receive the award. So this is kind of my personal story, but as I say, it involves really the work, the foundation of many other people. So what I'm going to tell you is just my little piece, but it's representative of a lot of work of other people. So anyway, my brief story is I was, as Murray Barrett said, I was a graduate student in Harvard from 65 to 70. I worked in the group of Norman Ramsey, who's there. That's me trying to get close to the boss, you see there. But anyway, at that time, this was not long after Norman and his close colleague, Dan Kleppner, had invented and demonstrated the first hydrogen masers. And I won't say much about masers, but the basic idea of hydrogen maser, that you create hydrogen atoms in the excited state. They go into a cavity and they radiate into this cavity. And this radiation can be detected, and that makes a frequency standard by counting the cycles of the oscillations of this radiation. So anyway, Norman wanted to kind of do all the hydrogen isotopes, so I took on the project of building a maser for deuterium, one of the isotopes of hydrogen. And I like to say I'm the only one, I think, in the universe that has this number memorized, because that was the main result of my thesis. But more importantly for me, I think these high precision measurements taught me methods to try to control the environment, the effects that affect in this case, the frequency of these atoms, and also the fact that here we were dealing with superpositions, the two states involved in the maser radiation, and in those experiments we typically the superpositions would last for about a second. Now there were a lot of deuterium atoms inside this cavity that were radiating, and they were essentially independent. So it was just a bunch of single atom superpositions involved in these experiments. But nevertheless, we were dealing with superposition in those experiments. So after my graduate work, I went to work for Hans Dehmelt, who he was interested both in spectroscopy of ions, atomic ions, and so this related to atomic clocks. But at that time, he was most interested in pushing an experiment to measure the magnetic moment of the electron. That is, all electrons behave, they have a property, they behave like small magnets. And the one interesting part about this, being able to measure the magnetic moment of the electron, it turns out using quantum electrodynamics, quantum mechanics theory extrapolated to well, in this case, to electrons. The calculations can be very precise. In the case of electrons, it can be calculated now to 12 decimal places. And so this was a very precise test to try to make this experiment to measure the magnetic moment of the electron. Well, anyway, one of the features of this, we started out with a group of electrons inside, and this is meant to be a schematic of the electrode structures. And in fact, this electron, or this group of electrons inside this metal structure, they behave like a tuned circuit. If you don't know anything, if you're not electronics minded, what you can think about is that there's these electrons in this trap, we call it, like marbles in a bowl. They can oscillate back and forth, and when we force their motion, in the case of this electrical analog, we induce currents in the electrodes, and the magnitude of those currents is proportional to the number of electrons in the system. Well, it turned out in these experiments, it became clear not long after this work had started that we would, for various reasons, we would get the highest accuracy on measuring this magnetic moment property of the electrons by just using single electrons. And one of the main reasons for that is if there's a group of electrons, when they bump into each other, they tend to disturb the measurement of the magnetic moment. So one of my main project when I was a postdoc with Entanglement was to try to isolate single electrons. And well, I guess I already said this, that it was important to get down to one because we could make the highest precision measurements. So what we did to do that, it's actually pretty simple in the end. What we would do is we would drive the motion of the electrons at a value where occasionally, in this example here, we started out with 7 electrons in the trap, and occasionally we'd drive it at a critical amplitude where occasionally one of the electrons would strike an electrode and be absorbed and lost, and so that would reduce the current, and we'd see these steps over time. And of course, the interesting one was when we got to well, you can see the last step here was when the last electron went out of this atomic bowl, you could say. And of course, the interesting case was when we would get down to this last plateau of a single electron and went on to do those kinds of experiments. Now, so this was just a precursor to the accurate measurements of the magnetic moment of the electron, and Desmont actually received the Nobel Prize later for his work on carrying out those measurements with his colleagues listed there. So anyway, also at that time, I was still thinking about lasers and atomic physics making atomic clocks. And so we had some ideas about how the atoms, how we could cool atoms using lasers. And also Hench and Challo had turned out, ideas looked a little different at the time, but they're basically the same. And I won't describe much about, really very little about laser cooling, but the idea of laser cooling, in a simple sense, we know that when atoms scatter light, they feel, of course, in some simple sense, each photon imparts momentum to the atom, and we can arrange the frequency of the lasers such that when the atoms only absorb and scatter light when they move against the laser beams, which slows their motion. So that was the basic idea of these schemes. And the reason that was important, we realized even at that time, we certainly didn't realize all the uses of this laser cooling, but one thing we knew about them is it's important in high resolution spectroscopy. And the reason for that is an interesting one, is that this comes from Einstein's theory of relativity, where, pardon me, he showed that, of course, time is relative. So for someone on a moving frame, time moves slower than, say, we at rest, an observer at rest. And this is important in the atomic clocks. For example, in this maser, the atoms are bouncing around inside this cavity they radiate into. And because they're moving, the time moves slower for them. And we have to calibrate that effect. So one way to do that was to slow the motion down with this idea of laser cooling. Anyway, after I finished this work, this preliminary work on the electrons, and then I went to the National Institute of Standards and Technology, which was then called the National Bureau of Standards. And my first task was, when I went there in 1975, was that NIST didn't have an operating clock, which is a bit of an embarrassment. So the first task at hand was to make the cesium beam atomic clock work. And so that's what I worked on for the first year and a half. And at that time, NBS was mostly a service organization. Its one main job was to provide the unit of time, the second, based on the oscillations, so-called hyperfine oscillations in cesium atoms. But the other functions of the group was just to do calibrations of other clocks. And but my boss at that time was Helmut Helwig. He had this vision that NBS then should be doing more basic research. So he got some initial money for us to support to try to do these initial experiments on this laser cooling. And so an interesting part of the story is that, so Hans and I had these ideas, and I knew that he had gone to work took a sabbatical, and he worked in the lab of Peter Toshek, who was then in Heidelberg. And so one part of this interesting part of the story, I think, is that I knew they were working on this because I know that Hans had gone to this lab to work on it. I'm almost certain they didn't know about that we were working on it. But so one interesting thing here is you can see these papers reporting these first laser cooling experiments were published very close together. But if you look more closely, the submission, when they were received at the journal, that their paper actually arrived one day earlier than ours. So I guess you could say they won this race. But anyway, but it was a pretty amazing coincidence that they, we really didn't have knowledge of where either one of us were on these experiments. So in these experiments, the Peter Toshek's group, they were able to verify the cooling because turned out they could hold, when they cooled the ions, they could hold them in the trap longer. In our case, we did something similar to what I had done with the electrons, and it turns out that rather than looking at the driven motion of the ions in the trap, we looked at just the thermal noise, the induced currents due to their thermal motion. And what was nice about that was these induced currents were directly proportional to temperature. So in this case, in this first crude experiment, we could see the cooling directly in terms of temperature. So anyway, this was our group at that time, and you can see that these are the main guys not very long after these first experiments on the cooling. I'm always embarrassed to show this picture because you can see my colleagues here, Wayne Utano and Jim Berquist, they look pretty much the same, but these other guys, I don't know, didn't really be able to recognize them. Well, anyway, our group got a little bigger in the meantime. This is our group last March, and we're benefiting from a lot of good young people working on these experiments these days. Anyway, after these experiments on laser cooling, it became clear also, as in the case of electrons, that for atomic ions we could reach the highest precision if we just had a single ion in the trap where we observing its its internal structure. And so in the experiments here, and in this case, Peter Toshek's group, along with Emil again, they clearly beat us to the punch on this one. They were about a year ahead of us. But nevertheless, both experiments we could tell how many ions we had in the trap. Similarly to the way we did with the electrons, we'd see in this case steps in the fluorescence when we scattered light off the ions. In the case of the work on barium done by Peter Toshek's group, they could actually, it's one of the very few ions that when you scatter light off of it, it's in the visible region of the spectrum. Most of the ions are in the ultraviolet. But nevertheless, if with some small magnifier, you can actually see a single barium ion. In this case, it's sort of a faint, looks like a faint star. It's blue fluorescence, and you can actually see it with your eyes through a modest magnifier. So actually, we went on. The ion that we tended to zero in on for these single ion experiments was Mercury. And the way schematically, the way those experiments would work, we had this transition that we would scatter a light off of the ion, and this was used for cooling and also detection, and I'll say a little bit more about that in a minute. But this schematically, what we had is we had this electrode structure, and inside we'd put a single ion, and then when we sent the laser beam through, we could see this fluorescence from the scattered light from the ion. So this is actually a picture of this apparatus here. You can kind of make out this part of what we call the end cap, and then the inner part of this ring structure here, and this is actually a picture of a single ion, and in fact the resolution, you can see the size of this blob there, that it's actually about 1,000 times bigger than the actual size of the ion, the wave packet that describes the ion, and we don't see the sharper picture there simply just because the optics is limited. The resolution is limited by the optics. And nevertheless, we chose this ion. And the reason for that was it also has a transition here which potentially makes a very good clock. And the upper state in this transition is fairly long-lived, which means that the range of frequencies over which this atom will absorb on this transition is a fairly narrow range. And so what I'm going to do now is give you the 30-second idea of how we make atomic clocks, and basically all atomic clocks work the same way. So before I do that, there's two ways to view this. We tend to take your pick, but one way we view these transitions in the atom is that if the atom will, if we started out in this lower energy state, and we shine it with this radiation on it. As I said, this upper state is very long-lived, and so it will absorb maximally or scatter light maximally, or absorb light at a very particular frequency. In this case, the frequency is over 10 to the 15th hertz, about a million billion cycles per second. But you can also think quantum mechanically, this is very much like it's an oscillating dipole, which you can think of very much like the oscillations of a pendulum and a clock. And of course, the main difference is that they oscillate many more cycles in any given unit of time. So the way we make a clock out of this is really pretty simple, if I can explain it right here, is that we basically have some oscillator. In this case, it's an oscillator that's going to produce radiation. And then we shine the radiation on the atoms that are contained in this example here in a box, and we do it with our ion traps in our experiments. And then we need some detector that tells us when the ions have absorbed the radiation with maximum probability. And what we do in the lab then is we basically describe how this is done electronically, but it's really pretty simple. We basically just look for the condition when this transition is made with maximum probability, and we just using when we detect when that condition is, we can feed back to control the frequency of the oscillator. And then the clock part is that all we do is we count the oscillations of this frequency counter to define a unit of time. And of course, the reason these days what we do is we like these optical transitions because basically we just get to count more cycles in any given time period, and we can divide it up into finer units. So that's why we think about these high-frequency optical transitions these days. Anyway, going back to our Mercury ion experiment, we want a way to detect this when this transition occurs. And basically what we do is we use the transition that does the laser cooling. And the idea is, let me back up here one sec. If we start the atom in its so-called ground state, if we then apply this radiation, if we're mistuned with the laser here, then the ion wants to remain in the ground state. And then what we do is we turn that radiation off and then turn this radiation on. And if the ion hasn't made this transition, then when we turn this transition on, we see the scattered light. On the other hand, if it's been promoted up to this level, when we turn on this laser here, the ion is up in this level, so there's no way for it to scatter light. So we have a nice way to detect this. And in fact, this detection is nearly 100% efficient. You can see in this example here, what we do is we capture a small amount of light, and the time here in for each one of these steps was about a millisecond. But you can clearly see that when the ion was in the ground state, we see fluorescence, and there's this very little fluorescence in the case when it's up in the excited level. In fact, this light here is just due to some background light scattered off from the input laser. Well, I'm going to summarize very quickly. There was a lot of work that went into trying to make a clock out of this. In our lab, Jim Berquist led this work on the single Mercury ion. Just a few features to maybe mention about this. The trapping, when we trap the ions, basically what it means is that at least on the average, their velocity goes to 0. And what that means is it gets rid of the so-called first-order Doppler shift, the effect that when used to be in the old days anyway, people do describe it when a train comes toward you, the whistle is high-pitched, and when it goes away from you, it's lower-pitched. And we have to worry about that effect, but just the trapping alone gets rid of that on average. I mentioned that this laser cooling suppresses the time dilation shift, and there's we trapped this ion in a device at low temperature, and there were several advantages of doing that. Anyway, after many years working on this project, we were able to realize that measure the frequency of this transition, which is given down here. And the thing we were happy about, this was the first clock that had a we say systematic uncertainty, that the measurement errors were below the best cesium clocks at that time. And I think most of us now making atomic clocks, we think that, even though the definition of this is still based on cesium, the length of time, the second, we think with these high frequency optical transitions, both with ions and with neutral atoms, that'll be it appears to be the way of the future. And I've only talked about our work here, but there's, just for the case of ions, there's many other groups working on these similar ideas to realize high accuracy clocks. And there's also a host of experiments based on neutral atoms that playing with these ideas. Okay, so anyway, just from there was two, from this point where we were doing these laser cooling, it was interesting to think about how we could control the quantum levels of motion. And the picture you want to think about, of course, the classical picture, if we have a single ion in the trap, it's going to oscillate back and forth. We know, though, in a quantum description of this motion, the atom actually doesn't, it can only exist in discrete energy levels. In this case, they're equally spaced. What these numbers mean is just the number of quanta, we say, in this harmonic oscillation picture. So what we would like to do, and to be able to control things, is we'd like to start the atoms, just freeze them out and put them in this lowest possible energy state. So one way we can tell what's going on is that if we think about, you can first think about the classical picture of the motion. If the ion is oscillating back and forth, if you sit in a reference frame with an ion, it appears to see the laser frequency being frequency modulated due to the first order Doppler effect. So in fact, when we probe the spectrum, by the way I described previously, we see a spike down in this central feature, and that represents when we're tuned right on the resonance of this transition, but it also indicates the fact that if the atom starts in this quantum level of motion, it goes up to the higher electronic state, but remains in the same state of motion. And these other features, this one we call the blue sideband, and what that represents quantum mechanically is that when the atom absorbs the radiation, it goes to the higher electronic state, but also increases the motional quantum number by 1. And conversely, when we're tuned to what we call the red sideband, that represents a case where we excite the transition and the motional quantum state is reduced by 1. So what this led fairly naturally into a way we could cool to the ground state of motion. And what we did in these experiments, we were able to set things up where after the atom was excited, the conditions of the experiment were such that when the atom re-emitted the photon and decayed back to the ground state, with high probability it would do it without changing the motional quantum number. And so to do the cooling, then the simple thing was that we would tune the radiation here to do one of these transitions where the motion quantum was reduced by 1, and then when it radiated, it would come down, and in the overall scattering process here, the motion quantum number would be reduced by 1. And basically all we did is we just left the laser tuned to the same place here, and the atom would walk down this ladder of quantum states until it reached the ground state. And of course, when that happens, the absorption stops because there's no n-1 level for the atom to go to, and so the process would stop. And this was also turned out to be a convenient way to tell when we had reached this lowest quantum level of motion, because these features that I described before, the one that describes this transition here, it would essentially disappear, did completely disappear. The experiment's not perfect, but you can see there's quite an asymmetry in the case where it absorbs a photon or a phonon, a quantum of motion, or where it reduces the quantum motion by 1. And this allows us to determine, at least on average, we've to a high degree cooled with highest probability the atom is in the ground state of motion. So I'm jumping around here a little bit, but I did want to come back to this idea of Schrödinger's cat and say how we made a simple version of this. And so what we did is in these experiments here, I'm changing notation here a little bit, just representing the electronic states by these arrows pointing up and down. And so in this case, we started the atom out in the lowest electronic level and with this laser cooling in the ground state. Then what we did is we would apply radiation connecting these levels to make a superposition of the ground and excited state. And it turns out this is a detail that takes quite a while to explain, but with lasers we can apply a force to the ion which only in this experiment only acts on the upper energy state. So what we did is we forced the motion of this part of the wave packet of the ion, or this part of the wave packet of the ion to start oscillating back and forth. So what I show here is a snapshot of the motion of this component of the wave function when it's at the leftmost extreme of the in the trap. And then what we did, just to kind of make the picture symmetrical, we shined radiation on the internal states to change the upper state to the lower state and vice versa. And then what we did is we applied this force again, which only acted on the spin up, we say, level, and we could end up with a state that at some instance of time looked like this. So here the particle is on the left side of the bowl, correlated with it being in the ground state, and simultaneously it's on the right side of the bowl, correlated with it being in the excited state. And so that's what I'm just writing here. And what we would say is this is very much like Schrödinger's cat. We're correlate. The idea here is that what was the state of the radioactive particle is very much like the state of the electronic states of the ion, and the more macroscopic particle is whether it's on the left side of the bowl or the right side of the bowl at the same time. And we're making this analogy here, and you could say, well, in fact, it was true in this experiment. It was a very small displacement of this particle. What I'm representing with these blue circles here is just the size of the wave packet that represents the ions. And you can see we're only displacing it or making the distance be about 8 times the size of this wave packet. And you could say, well, this is too small to really call it a Schrödinger cat. But one of the dilemmas we still have is the one that Schrödinger was faced with. If you say it's too small, then you have to say, well, what's big? I mean, in principle, we can't, for various practical reasons, we can't do this. But in principle, we could, make it one part of the wave function be over here and another one separated by 10 centimeters, which is very macroscopic. And if you say, so this is too small, then you have to say, well, how big does it need to be? And there's no really way to do that. So we would say that, in fact, even though it's a small object, it still very much has the same properties as Schrödinger's cat. Okay, so let me say a little bit about quantum information. We'd certainly gone on, we still go on with these experiments, trying to realize better and better clocks. But in the mid-90s, there were some earlier ideas about these ideas of quantum information processing, but it really took off in the mid-90s when Peter Shor, a computer theorist, cooked up this algorithm which said that basically if you could construct a quantum computer, you could efficiently factorize large numbers. And the reason that got a lot of activity was that I think certainly probably most of the people in this audience know, but for those that don't, basically almost all encryption we use today, the secret coding, is based on an algorithm which would be compromised if we could efficiently factorize large numbers. So you can imagine, for example, various intelligence agencies get real interested in things like this, and it has fueled a lot of the research in this area. And for atomic physicists, one interesting story was that in Boulder in the mid-90s, there was this a well-known atomic physics meeting that was held there, and we invited Arthur to come. Arthur was well known in terms of, for example, these ideas of quantum communication, but he knew about this idea of factoring, so we got him to come there to give us a talk and explain this to us. And so I'll just say a few words about quantum computing, and I apologize. I know there's some experts in the audience, but the reason this looks interesting is that, again, we're going to play on this idea of superposition. So a classical bit, we know it can have one of two states. But in these quantum systems, like the two energy levels of our Mercury ion, we can put them in these superposition states where it holds both the value of 0 and 1 at the same time. And the reason that, pardon me, one reason you can see why that might be interesting is if you play along with this idea that we're able to store both states at the same time, what we see is this exponential scaling. That an example here is if we have 3 bits, then a classical register would store one number, say 101, but in the superposition state, a 3-bit register can store all the numbers from 000 up to 111. That's 8 possibilities, or 2 to the 3. So what that says is that for n quantum bits, we can store 2 to the n numbers simultaneously. And a dramatic example is that for, say, 300 bits, in a classical machine, I might store a line of text, but in this superposition sum, that would store 2 to the 300, or about 10 to the 90th numbers simultaneously, which if we made a classical memory based on that, it would require more matter than all the matter in the universe. So that sounds pretty good. The other thing is that when we do these operations, which I'll briefly describe, we actually can operate on all these numbers at once. So we can do all these, there's this idea of massive parallelism. But if you remember back to the simple cartoon example of the boxes, this also applies here when we have many particles in this larger superposition. When we finally go in and, although during the process, the computer is actually working on all these numbers at once. In fact, when we measure something, everything collapses down into one of these possibilities, and these coefficients I put out front here represent the probability in a mathematical way that say this number might be represented or might be measured in the final measurement. So this restricts the possibilities. You know, we get these nice features, but we have to live with this quantum rule that we only get one answer in when we do the final measurement. And in fact, Peter Shor's algorithm realizes is an example of a cleverly constructed algorithm that can utilize these properties and also satisfy this rule about quantum mechanics. So I won't say very much about gates, but let me just briefly say that there's some direct analogies. In a classical computer, although it may not be the most efficient, it could be composed of 2 gates, a bit flip and, for example, an AND gate. Doesn't have to be that one, but you can construct it out of these 2 elements. And in the quantum world, what we want to do is rather than just bit flips, we want to do something we can call rotations, and that's what generates these superposition states. And we also want to do some logic gate. Here's a particular logic gate which we can realize with classical bits if they're in particular states. But this logic gate also applies to superpositions where the power of the quantum computing comes in. Anyway, let me get back to our world in the lab. What was interesting, this talk that Arthur gave at this meeting, both Ignacio Serac, who's in the audience here, and Peter Zoller, they were, I think one of their strengths as theorists is that besides being very clever at the theory, they also know, they keep well tuned into what the experiments can do and what they can't do. And anyway, after hearing this talk of Arthur's, in a very short time, they were able they actually made a proposal for how you could make a quantum computer, and it was based on ions. And this was really the first proposal, a comprehensive proposal, how you might realize this in a physical system. So I'm just going to say schematically how this idea works. So here we have what these bars represent as the electrodes from a trapping structure. And in this example here, we store in 5 ion qubits in a line here. What you can think about is that we have this ion trap structure. It makes a 3-dimensional harmonic well that is this bowl, and what we in such a way that along this horizontal direction, the strength of the bowl is relatively weak. So the ions want to line up. They all want to fall to the bottom of the well when we cool them, but the Coulomb repulsion between the ions hold them apart into a regular array. And then what you can think about is this collection of ions looks kind of like a pseudo-molecule. You can think about its vibrational modes. And so their idea was the following. The frequency of these modes in general tends to be different, and we can spectrally isolate these different modes. So the simplest one to think about is where these 5 ions are all oscillating back and forth together. But the key thing about that so-called center of mass mode is that it's shared amongst all the ions. So their idea was the following: in general, the ions will be in some entangled superposition of the internal states, and the idea to perform a logic gate between 2 quantum bits is that you utilize the fact that this motional mode, we can think about its ground and first excited state as being another quantum bit. So the basic idea of their scheme was you take a laser beam and you focus on this ion here, and if you can, then the idea was that you first transfer the superposition of this ion you just transfer it into this motional state. And then because that motion is shared amongst all the ions, if you can somehow do a quantum gate between this motional quantum bit and the internal state of this ion here, then basically you've done a gate between those 2 ions that you address with these laser beams. So I'm going to give you some idea how this works. This picture I'm going to give you is a little incomplete, but it'll give the flavor of how these quantum gates work. Pardon me. So let's suppose we've done this first step. We've mapped the internal state of the first quantum bit into this motional quantum bit. So I'm saying that that superposition is represented by the fact that both of these states motional states are in a superposition, and of course, in general, the internal states won't be in some superposition. So we have what we'd call an entangled superposition comprised of the internal states and the first 2 energy states of the motion. And the way you can, if you think back to the Mercury example, the way you can see how the logic works is, let's suppose we call the motion bit the control bit, and we want to realize this part of the truth table where if the motion is in the excited state, then that we can flip the internal state bit. If it's in the ground state, then it remains in then the internal state remains in the ground state. And the way we do that is just in this simple example is we tune the laser so that it takes this amplitude and puts it completely up to that level there, which means we flip the bit. On the other hand, just like in the laser cooling case, there's no way to drive if the motion is in the ground state, we can't drive this transition, so the internal state remains the same. As I say, this picture is a little incomplete, but it gives a flavor of how the logic works. And anyway, at this time, what was nice for us after this idea of Ignacio Serach and Peter Zoller, we were playing games with these quantum states, and we were lucky to be in the right position. So fairly quickly, Chris Monroe was on our group at that time. We could kind of jump on this experiment, and we were able to demonstrate this quantum gate between the motion and the internal state. So I'm going to, as I said, this tale is a little egocentric. I'm only talking about work of our group, but I want to give you some flavor for where this is going these days. First of all, there's been a lot of demonstrations of algorithms. You can kind of think like that's a subroutine in a classical program. In our lab, Didi Leibfried has led a lot of these algorithm demonstrations. Something very interesting that I really won't have time to talk about, but I think one of the, starting with the first ideas of Richard Feynman, he had the idea, well, you know, because of the way the required information scales with quantum systems, this exponential scaling, his idea was, well, for large systems, why don't you try to get one quantum system to mimic another? And that's this idea of simulation. So a lot of groups are working on that, and I won't, as I say, I won't have time to describe that, but I think that's one of the things that as physicists we look forward to try to realize this idea of simulation. And one thing to say is that it turns out this problem of factoring is really what kind of got the field propelled going forward in a big way. But it's probably also the hardest problem anybody has thought of, that is to be able to do it on a practical scale. Whereas I think we're hopeful that with a modest number of ions, maybe somewhere between 10 and 100, we can do some simulation that is intractable on a classical computer and tells us something interesting. And I think my friend and competitor and colleague over many years, Rainer Blatt, his group has done has the highest fidelity, we say, lowest error quantum gates, also based on ions, and he's been able to do he's been able to do a simple demonstration of this universal quantum computer that might be applied to simulation. So, but anyway, as I've said earlier, there's many more people working on these problems, and just to give you an idea, this is just I list the groups that I'm currently aware of that are only looking at atomic ions to realize these ideas, these simple ideas of quantum computing. So you can see it's a big enterprise. And then there's also, of course, many other possible physical platforms, superconducting Josephson junctions. There's many other possibilities. So it's a pretty big industry these days trying to realize some of these things in the lab. Just to give you an idea what these ion trap experiments look like, as this is one of our labs. So our quantum computer occupies this tiny volume over in one corner of the room, and where all the work goes in is adjusting these lasers, trying to get them to do what they're supposed to do, and they never do it. So, you know, so you get maybe, you know, you work months setting up, say, to demonstrate some algorithm, and the experiment will work maybe for a few hours where you can get the data you want. Let me just say a little bit about these ion traps. This picture I showed earlier, I showed this idealized structure before. It turns out that we'd like to make these traps smaller, and the main reason is that things speed up, and the reason is that for given applied electric potentials that we make these potential wells, the frequencies go up basically as 1 over the dimension squared. So we want to make things small. So in that first picture I showed that was the introductory or cover slide, I showed this picture here, and each one of these what we've done here is we've distorted these electrodes into a plane, and ions can be held above this plane. And each one of these little tiny squares is a place where we can store one or multiple ions. And in this thing here, we were trying to demonstrate a way that, you know, you could to scale up, where you could actually move information by moving the ions at various locations in this structure we call the racetrack. And there's many groups working on this, the microfabrication. There's some real professionals like at Georgia Tech and Sandia that are doing these kind of things. So anyway, there's a lot of work going in just to this particular scheme where you move information around moving the ions. So I want to close out by just saying a little, coming back to the clocks. Lately, this project, which has been led by Till Resenband, he's recently joined by David Leibrant in our group. Anyway, think back to the Mercury example. It's very similar case as to the Mercury. In this case, the upper state is even longer lived, which means the range of frequencies over which the ion will absorb the radiation is even more narrow. Now, in fact, in principle, we could detect when the ion makes the transition, just like we did in Mercury. The problem is that this is at a really relatively short wavelength, where we would like a continuous wave laser, and although these short wavelengths are starting to be made, Jun Yi, who's in the audience here, is certainly one of the pioneers of going to these very short wavelengths. But in practice right now, it's hard to get a continuous wave laser at these short wavelengths. So what we do is what we've been able to take advantage of is this idea of, you remember the first step of this scheme of Serac and Zoller, where you take this information, the superposition that's in the internal state, and map it onto the motion. What we do here is when we start the ion, the clock ion in its ground state, and then we drive this transition, before we do the measurement, in general, it's in some superposition of these states. So what we do is we map this superposition onto a motional mode of two ions in the trap. Here we've included a magnesium ion. Then what we do is we map that superposition onto this internal state superposition of magnesium, and it turns out magnesium is one where we can easily do this detection. There's actually a lot of other side advantages of doing this in addition to this detection technique. For example, while we're irradiating this ion here, we can continuously cool the ion by laser cooling the magnesium. The radiation we need for that is detuned far enough from the levels in aluminum that it's not perturbed by this cooling radiation. Anyway, there's many things I won't go into that are interesting about this, but right now we're down to a level where we call the systematic uncertainty, the uncertainty, the error due to things that in the environment we can't completely control. The errors expressed fractionally are about a little under part in 10 to the 17. And what I'm going to finish here with was an example, another example where this is interesting, and that at this level of precision. And it also comes from Einstein. So I mentioned this idea of the time dilation shift that came from Einstein. There's also another effect that comes from general relativity and also comes from Einstein. And the fact is that reference frames that are in different gravitational potentials run at different rates. And in terms of the clock, it turns out on the surface of the Earth, if a clock is, if you have two clocks, say they're at the same height initially, you raise one by 10 centimeters, it turns out the one that's raised by 10 centimeters will run apart in 10 to the 17 faster than the lower one. So it's effect that real effect that we have to take care of on this kind of human scale. And as a kind of a cheesy demonstration of that, we had two clocks based on aluminum. So this shows the optical table for one of those clocks. In another room, there's another aluminum clock, and they were at the same height in the lab. So the relative frequency shift between the two started out as 10 to the minus 18. So James Chow here made this portable clock, which you can see. The cheesy part is we put jacks under this table, and then here's James raising the table up, and you can see what we predict the shift to be. He finally puts it in place there, and then we could compare the frequencies of the clock. And of course, the errors in this demonstration were fairly high, but nevertheless, we were consistent with this so-called gravitational potential redshift. Actually, one of the things that's was always kind of disappointing to me is that after my whole career has been spent a lot on atomic clocks, and one of the disappointing things for me is that with this gravitational potential redshift, one of the problems is there are ways to independently determine the gravitational potential. And but unfortunately, those methods of determining the gravitational potential expressed in terms of height on the surface of the Earth, for example, in Boulder, partly because of the mountains, the uncertainty in the height is, in terms of this gravitational potential, is only known to about plus or minus 30 centimeters. So what that means is if we want to do accurate comparisons of clocks, the only way we can get down to these levels of part 10 to the 17 and below is the clocks have to be in the same location. Otherwise, we can't extract out this gravitational potential redshift. So the disappointing part about this is that in the end, after all this work, is that, I ended up with kind of a fancy height indicator, So now it isn't quite so discouraging. Actually, Till Rosenband, who's led this project, he's taking the high road here. This is a way to maybe do geodesy, that is, measure this gravitational potential redshift. And there are other interesting applications. So I just want to conclude and say that, conclude my story. These are the guys I've worked with over the years on these, what I want to say is that in the late, starting in just in the latter part of the 70s, I basically worked with Jim Berquist, Bob Schrodinger, and Wayne Atano my whole career. And then John Bollinger joined us in the early 80s, and then I talked about the younger guys that joined us in the meantime. But of course, as nice as it's been to work with them over the years, we certainly relied on very large numbers of good students and postdocs and visitors, numbering over 100 certainly by now. And pardon me, at NIST I've been really lucky because great bosses over the years. These are my group leaders, and one measure or one thing I like to point out, my boss's boss, Catherine Gebbe, she was the leader of the so-called physics lab for the last 20 years, and I'm the fourth person after Bill Phillips and Eric Cornell and Jan Hall to receive the Nobel Prize. So he, under her, well, she was director of the lab, so she's been doing a good job. And of course, we've had a lot of support from the agencies too. So I'll say a couple words about the Nobel ceremonies this last December, and it really is it's a very fancy deal. I mean, this is a once in a lifetime thing for certainly most physicists, and it's very elaborate. So this was the award ceremony. You can, over on the left side, this was the group of, there were 9 laureates this year, and there's some past laureates behind us there. These are primarily officials in government and the Nobel Foundation, things, Swedish Academy of Sciences and so on. And this is the royal family here. So, so I mean, it was an almost surreal experience for us to receive the award from the king. And anyway, so after this nice ceremony, the king and queen had a few people over for dinner. And one thing that always amazes, it's interesting to think about. So basically, it was a wonderful experience, but one of the unfortunate things is each laureate, we were for these fancy events, we were restricted. We could only invite 12 guests. So this included, out of that 12 had to be family members and group members that you wanted to bring along. So one of the unfortunate parts, you couldn't invite everybody you want. But anyway, if you do the numbers, so the laureates and their guests, who were at the main table with the royal family and the government officials, the laureates and their guests was only about 100 people. And this is 1,200 people at this banquet. And one thing it tells you is that this, not surprisingly, I mean, it's a very important event for, Swedish society and officialdom. And it's something, obviously they want to hang on to, and that's why they do it in such a nice way. So it really was a great experience. And I just want to conclude by saying one of the nice things for me was that I've known Serge's physics for at least 35 years, and we became friends about 25 years ago. And our wives have also become friends. So it was really nice to be able to share with him. So with that, I'll conclude. Thanks.